Aujourd'hui, nous avons le plaisir de recevoir Bruno Sicardi pour ce séminaire IAP. Bruno est spécialiste de l'étude, de la recherche, de la modélisation, de la dynamique des petits corps dans le système solaire, des anneaux dans ces petits corps, des atmosphères dans ces petits corps. Il mène beaucoup de campagnes d'observation dont il parlera aujourd'hui pour les observer par occultation. Bruno est professeur à Sorbonne Université, anciennement Université Pierre et Marie Curie. Avant, il a travaillé à l'Université Paris 7. Il a travaillé également au Brésil. Il est toujours professeur. De nombreux étudiants, notamment moi, l'ont eu comme professeur et ont découvert l'enseignement de l'astrophysique avec lui. Je pense qu'il y en a beaucoup dans ce cas-là, donc c'est un très bon souvenir. Et puis donc il mène de nombreuses campagnes d'occultation dont il parlera aujourd'hui, ce qui en fait un petit peu le successeur donc, des aventuriers en astrophysique, avec le capitaine Cook, Guillaume Le Gentil, Arthur Eddington, qui partaient très loin pour mener des observations.
Je suis revenu quand même.
Et qui revient en plus pour nous présenter des résultats aujourd'hui. Je t'en prie, Bruno.
Ok, merci. Donc je vais parler des résultats obtenus dans les dernières années via ce qu'on appelle le phénomène d'occultation stellaire, et en mettant en perspective tout cela avec la mission Gaia, qui a énormément augmenté le taux de succès. C'est bon là? Ah, okay, in English, sure, okay. So the observation of stellar occultations and put in perspective with the recent results of the Gaia missions. What's an occultation? As you know, a planetary body is moving in the sky, and from time to time, this body will come in front of a star, so we call it an occultation. Here is an example from San Pedro de Atacama in northern Chile, and if you are careful enough, you can see that this star will disappear for a few seconds when in this case, a dwarf planet, Quaoar, is passing in front of the star. So you don't see any more Quaoar because it's very small and very faint, but you do see, or you do not see the star, which is actually the moment when Quaoar was in front of the star. And as Quaoar is basically opaque, the star disappears. So I've been applying this technique for studying the outer solar system. More precisely, the Trans-Neptunian region, so the Kuiper belt and then Trans-Neptunian, and maybe someday, and we are studying that, observing also the Oort cloud through stellar occultations. There are many things going on there, so I'm basically interested in those bodies beyond Neptune. So this is a logarithmic scale, and in all these regions you have thousands of bodies. Some of them are dwarf planets, so big enough to assume a spherical shape. Very small bodies, down to fraction of a kilometer, a few meters, dust. And some of them are big enough, comparable to Pluto. Some have atmospheres, like Pluto, some have rings. So it's an old field of studies, and it's a pretty active region because it kind of remember the first times of the solar systems where the giant planets were migrating, throwing away those bodies, and some original bodies formed there. So it's a whole history of the solar system which is stored there. In terms of composition, but also in terms of dynamics. So knowing them better, like size, density, composition, is giving us keys to the formation of the solar system, and more precisely that region of the outer solar system. So what is an occultation doing? So this is a highest resolution image of Pluto taken by the Hubble Space Telescope. So you can probably do a bit better now with instruments like SPHERE at ESO, but basically you'd have a resolution at Pluto of 100 kilometers from the ground, from the Earth. To give you an idea, this is the moon observed at the same resolution of 500 kilometers. So the stellar occultation is scanning actually this body. It's very efficient. Why? Because when you scan the body, you just follow the star, and the resolution is not depending on the seeing, but depending on the time resolution. So if the body is moving 10 kilometers per second with respect to the star projected in the sky's plane, then 1 second is equivalent to 10 kilometers, which is much, 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 much smaller than any image. Also, when the body has an atmosphere like Saturn or Pluto or Triton, Neptune, the ray is bent by the refractivity of the atmosphere. So it's like gravitational bending in galaxies, but except that in this case, the bending is caused by refractivity, not gravity. But it's the same process, and you can detect this bending and the drop of signal associated with that bending and get extremely sensitive detection of atmospheres down to a few nanobars pressure level. So to illustrate that, here an occultation was observed in 2001 by Titania, which is the largest of Uranus satellite. And this was observed from Europe, Caribs, South America, Atlantic Ocean. And each observer observed the star disappearing behind Titania for a certain amount of time. And if you move on Earth by a certain amount of kilometers, then you move the observing chord by the same amount, because the rays are coming from infinity and are parallel. So each observer recorded the ingress and exit time, and then reconstructing this, you get the shape of the body, which is Titania in this case. Another interesting issue here is that you see that the chords were observed, they were shifted with respect to the predicted position of Titania in the sky. So it's a very efficient way to increase the accuracy of the astrometry. And to give you an idea, the angular diameter of Titania is 0.1 arcsecond. So if you do astrometry, classical astrometry, the PSF will be 1 arcsecond. So to get the position of Titania with that accuracy is just impossible through classical imaging. So one other aspect of occultations, besides giving very accurate shapes, is to give very accurate astrometric positions. And thus, to illustrate that, this is a fit to all the chords, and here is a distance along the limb of Titania, and this is a topographic features observed by Voyager in '86 with mountains and canyons, and this is the radius we got for Titania, and this is a radius by Voyager, with the gray region being the error bar of Voyager, and we get actually a better radius with a smaller error bar, and most of the dispersion, the deviation we see along the limb of Titania, all these smallish disagreements are caused by topographic features. So not only we can do a global fit, but you can do some geology actually and see features on the surface. This is another example, which is a campaign that people from EMCC, François Collat, and other people in the United States to detect the occultation by Antiope. And there are many amateurs, basically, scattered the west of USA, and they observed the occultation by the two bodies, the binary component of the body. So you can see that very small, this is about 50 kilometers, and irregulars. So you can not only detect that the body is binary, but also have the shape, very accurate shape of each component. So the science to time ratio is very high, because those occultations last for about a few seconds to a few minutes. And it has been actually the source of many papers, and including in Nature, like the discovery of incomplete rings around Neptune in '84. So the pieces of rings named arcs discovered by stellar occultation in the '80s. Then the measurement of the obliteness of Neptune atmosphere, and then the wind regime to create this obliteness. Detection of more matter around Uranus and Neptune. The probing of Titan's atmosphere with detection of gravity waves, not gravitational waves, but gravity waves moving in Titan's atmosphere. I will show that for Pluto later. So it's atmospheric science, where you see the fluctuations in the atmosphere of Titan. The size, very large changes in Pluto's atmospheric pressure, which is a seasonal evolution over decades, which was detected by occultation and can be only detected by occultation. Then this was the size of its satellites, Pluto's main satellite, Charon, which was made years before the New Horizon flyby, and the size actually for Charon was a couple of kilometers away from the average size detected by New Horizons. So we could detect years before actually the shape and size of Charon to within a couple of kilometers accuracy, which is a good way. I mean, it's not a huge result, but is say that if we observe the body from the ground and then from a spacecraft, we obtain the same figures. So it's a very nice and strong confirmation that the method is working. Then the radius determination of Eris, which was far away, it's about 100 astronomical units from Earth, and it was claimed to be bigger than Pluto when it was discovered, and it was the main cause for the renaming of those bodies as dwarf planets, and Eris was thought to be quite bigger than Pluto. So instead of adding more and more planets, this dwarf planet category was created. And during this occultation, we actually showed that Eris is a bit smaller than Pluto. So some people were very happy because they wanted Pluto still to be the biggest of those bodies. But a very interesting results from physical point of view, that Eris being smaller than previously estimated show that it's extremely bright. And it's so bright that it's brighter than fresh ice, actually. So it's covered by a very bright coating, which is probably a frozen atmosphere, which froze onto the surface. So it's kind of atmosphere which appears when Eris is closer to the sun. Then it evaporates, it sublimates, and the atmosphere will appear, and then the surface will be darker. And then when Eris is going far away from the sun, then all this atmosphere is collapsing again and creating an extremely bright surface with an albedo of about 1, which is observed only in some of those Saturnian icy satellites. Well, this is the size of Makemake, another dwarf planet, and atmospheric constraint. We didn't detect any atmosphere down to a very small level. Now, the discovery of rings around a small body called Charikla, which are orbiting between Saturn and Uranus. And this was a big surprise, actually. So it was the first time that we were observing rings, not around giant planets like Saturn or Jupiter, but around a very small body, which is about 250 kilometers across. So it's kind of biggish asteroid, but not a planet. But still, it has rings. And 3 years later, we detected another ring around another body called Haumea, which is a dwarf planet, whose biggest size, it's very elongated, as I showed after, is larger actually than Pluto. So it's very elongated, so it's rotating very fast, and it has rings too. And this triggered dynamical studies on rings and dynamics of disks around small bodies and irregular bodies, which was published this year. So the ring dynamics around small bodies. I will briefly mention that later. So the main difficulty of stellar occultation, even though they're very efficient, is the predictions actually, because the star is essentially a point source in the sky, and these are the sizes of different bodies, not in terms of real linear sizes, but in angular sizes. So, for instance, Eris is as big as Pluto, but it's farther away, so it appears as being smaller. And its typical size of those bodies are some 10, 20 mass milliarc seconds, which is about 10 to the minus 7 radians, so it's extremely small. So the main bottleneck of this method in the previous years has been prediction. So you have to basically observe a stamp at about 150 kilometers and know where the stamp will be and where the star behind it is months or weeks in advance. And as I will mention later, actually now, so before Gaia, the uncertainty was about this size, so we were missing a lot of events. And now with Gaia, we are able actually to have an accuracy which is comparable to the indentation of the stamp. So not only we have the occultation by the stamp, but we can pin down the prediction so that we're able to look at a specific indentation in the stamp. So it's really changed a lot, the perspective of those observations. To have another way to see that, this is here time, years. And this is a declination of Chiricahua in the sky with respect to some reference ephemeris. And you see here the motion of Earth, so it's 1 year, the motion of Earth around the Sun, which creates this wobbling there. And the dots are classical astrometry measurements, so you take an image with stars and Chiricahua moving the field, and then you pin down the position of Chiricahua with respect to the stars, and then you use catalogs. And then you say, okay, Chiricahula's ephemeris is shifted with respect to the reference ephemeris by this much or that much. And then you fit a new orbit and a new ephemeris. But you see here is about 100 mass. And now with Gaia, actually, you barely see actually the error bar on the new ephemeris. So each yellow point here is a detection of an occultation by Chiricahua. So we know where Chiricahua was very accurately. It was in front of the star. And because of Gaia, you know the position of that star very accurately. And because Gaia is global, it's 4 pi stereograms. If you know where Chiricahua is in the sky at a given moment, then you'll know where it is later. Because two stars are linked with a very high accuracy between themselves. So there are no more catalog errors as before, where the catalog were locally good, but you cannot patch up all the sky with a unique catalog. And this is the size of Chiricahua here and the size of the rings. So before, the error bar was such that we had about 30% probability to get the body of the rings. And now we have kind of 100%, because the 1 sigma error bar is inside the body of Chiricahua. So this is an example. In 2015, we organized a big campaign in Namibia, South Africa, to observe the shadow of Chiricahua and the rings, dotted line there, but nobody observed nothing. So it was a huge waste of money, time, CO2 emission, just to get nothing. And probably the shadow went up north or somewhere in the ocean here. So this was pre-Gaia accuracy, which was accurate down to 40 or 30 or 50 milliarc seconds. And now the situation changed. In 2017, we used a DR2 Gaia catalog. So this was a shadow of main body, the Chiricahua main body, and the blue lines are the limits of the rings, the span of the rings. And the error is this red dot here. So it's 10 kilometers. So instead of before, we knew that it was going over South America, but not really Chile or Peru or Bolivia. Now we know it's going over Chile, we know it's going over Cerro Tololo, over La Silla, and then there are some portable stations, so we told some people, could you move 5 kilometers north, could you move 10 kilometers south? So because we want to have this side of Chiclo, the other side of Chiclo. So not only we are getting the occultation, but we are choosing the places we want to study and say, okay, we want to study one part of the ring, the other part of the ring, the western limb of Chiclo, the northern limb of Chiclo, blah, blah, blah. So now this requires a lot of observers, so either big telescopes or very small telescopes using observing kits with a GPS, camera, some adapters, acquisition, PC machine, and it all fits into a suitcase that you can bring up in a plane and go somewhere. So sometimes the star is bright enough that a 25 or 30 centimeter telescope is enough. And so I got an ERC project funded 5 years ago called Lucky Star, which has a page with the general presentation here, so you can find it easily on using Quant or Google, with results, publications, presentation, and predictions. And those predictions are public, so we are working with people, in collaboration with people, or even some people are using those predictions but not collaborating with us because this is public. And I've been working basically with people in Spain, Granada, José Luis et al., and people in Observatorio Nacional, Rio de Janeiro, with Roberto Vieira Martins. Many amateurs under the umbrella of the International Occultation Timing Association, which is an amateur association. And for a while with a national Tsinghua University in Taiwan, and many observers. So maybe there's something like 150, both professionals and amateurs. So amateurs which are expert enough to observe, reduce the data, and have a professional approach to the observation. So they know well their instruments and how to set up the time. So sometimes I'm much more expert than any other professional, because you go to an observatory and you just ask someone to observe for you to point a telescope. And those people are in the middle of nowhere. They know how to point a telescope, how to acquire data, as to how to optimize the setup of the camera, how to set up the time very accurately, and some of them having using good photometric packages to provide light curves. So this project has several work packages: ring dynamics and discovery, observations of very small TNOs far away from the sun, Pluto's atmosphere, and some specific targets. It benefited from two important things. First, the launch of the Gaia mission in 2013, and then the first Gaia star was published for Pluto occultation we observed in 2016. So it's a DR0 release. So it consisted in only one star. So the Gaia project extracted from their preliminary catalog one star, which was to be occulted by Pluto on that date, and we wanted to have more accurate predictions. And we were anxious to get the occultation, and they were anxious to know if Gaia was working, because it was the first star ever used for prediction. And then it was good to something like 5 milliarcsecond, which was typically the accuracy of the catalog at that time. So everybody was relieved. And then after some time, we have been observing several stellar occultations. This is time here, and this is a number of chords. By chord, I mean a positive observation. So if a body is observed with one chord, it's one chord, and somebody has sometime observed with 3 people observing with 3 chords, so it counts for 3, blah, blah, blah. And this is in green here, the detection of quartz by the Lucky Star project, and in red by all other teams in the world. Two group, one in MIT and the other one in Boulder, Colorado. So you see that the Lucky Star has been really had a very active and broad, and it's now lead in the detection and study of stellar occultations with many bodies observed. So these are several examples of body we have been observing using stellar occultations, in green by the Lucky Star project and in red by other groups. So some of them have been observed only once, so we have little information, and some have been observed many times, like Pluto. So it's a bit misleading, but still, it showed that we have been very active and studying many of those bodies, either dwarf planets, but also small bodies. And we have been observing, actually, all the dots here are bodies that we have been observing in using stellar occultation. This is semi-major axis here and eccentricity here. So here you see, for instance, the Plutinos, so body which have a 3-to-2 resonance with Neptune, which is around here. The scattered disk of trans-Neptunian objects, some Centaur's bodies here. And now we are starting to study very small Jovian satellites and also Trojan satellites, Trojan asteroids, excuse me. So they are very small, so it took longer to get accurate enough predictions. So now we are starting to fill in this part of the phase space. Knowing that many of those observations are made by portable telescopes. This is something done 2 years ago. Here's a German amateur who traveled and was supported by the Lucky Star project and carried a portable telescope in the middle of nowhere in Namibia. It's a 50-centimeter telescope built in Germany with a kit I showed before. And he observed an occultation by cherry claw. So here you see the main body with some spurious effect there and there. So it lasted for about 1 minute, and before and after that occultation by cherry claw, you could see the ring, the main ring. And if you zoom out this ring, you see a double U structure, which is actually not noise, because you have been observing this double U structure several times. So not only we can detect the rings, but you can also detect substructures, and it's very important in terms of dynamics. How is it that the edges are so sharp? Why is it that sometimes the ring has 2 components, and on the other side of the planet it has only 1 component? So it means that it's probably a resonant cavity with material bouncing back and forth between very narrow and sharply defined edges. So just to give you an idea, actually, this is cherry claw, and this is Haumea, around which we have discovered rings too, at the same scale, angular scale. So even though Haumea is much bigger than cherry claw, it's farther away, so it's not much bigger in terms of size. But this is here the dithered Hubble Space Telescope pixel projected at cherry claw. So if you took an image by Hubble, you just barely see the size of cherry claw. You don't see actually the size of cherry claw. It's basically a stellar PSF. You kind of guess it's not a point-light object, but for sure we couldn't detect the rings using Hubble nor sphere. But remember that the previous slide, this guy in the middle of nowhere in Namibia with a 50-centimeter telescope detected the body, the ring, and substructure in the ring, which is kind of impossible. It's absolutely impossible with any imaging system from the ground, or even with ELT in the next few years. So this is to show you the power of this method, knowing that you need to move around. So you cannot stay home, but you have to organize campaigns. talking about that, there was an occultation 3 weeks ago by Charon, which is similar to Charikla, which was observed near Parc Montsouris by an amateur on his balcony with a 25 centimeters. So when I say you have to organize campaigns, this includes campaign in Paris, downtown, and center. So we have, with Gaia now we can afford observing with big cities because we can select and then tell people, oh, you're in London, just observe from London, don't move. So this is just a few slides on an object, a trans-Neptunian object, which is not spherical. This is in orange a spherical limb, the circular limb. And we see the actual limb is not circular. We observed here last year an occultation by a centaur object, so in the same region as Chariklo, and to our surprise, it appears to be extremely elongated. So it's kind of biggish. It has a major axis of 300 kilometers, but it's a cigar-shaped object. So just to tell you, here is a mixture of amateurs and professional observations. And then there was an occultation observed from Europe 2 years ago, which allowed the discovery of rings around Haumea, which is here. It's very elongated body, observed from different places in Germany, Hungary, Italy. And the interesting thing is that we could measure the size, the 3D size of Haumea. So we know it's elongated because its rotational light curve is very variable. So we get the ratios of the different axes, and then the occultation gave us the actual size at one moment, so then we can extrapolate the 3D shape using both the occultation and the rotational shape. And because it has satellites, we could we know the mass of the body, and from the mass and the shape and the size we get the density. And an interesting issue here is the density is much lower than allowed by what's called the Jacobi solution. So if you take a rotating body in equilibrium, which is homogeneous, it will assume a certain shape, and the shape is related to the rotation period that we know and the density of the body that we are looking for. And using that trick, we determine the density of 2.5 if Haumea is a homogeneous ellipsoid, and we get 1.9, so it's much less. So if it were a body in equilibrium and homogeneous, it should fly apart because it's rotating too fast. So it should kind of, explode in space. So being much less dense than expected from the Jacobi homogeneous solution meant it's probably differentiated with some rocky core and an icy mantle. So something we started to do with people at the MCC, like Nicolas Rambaud and other colleagues, to explain this discrepancy between the Jacobi solution and a more realistic differentiated body. So it's the first time that really start to do some geophysics of those bodies, like, it cannot be an homogeneous body, so could it be a mixture of silicates and ice, and what is the ratio of ice to rock? Another interesting result is that another trans-Neptunian object, AZ84, which was serendipitous, but it was observed from Thailand, from Japan, and from China. And this observer here in Yunnan observed a disappearance of the star very gradual. It lasted for more than 12 seconds. And usually it's very abrupt because it's a very sharp screen. And the interpretation of this was not predicted because it was pre-Gaia result, but the main most probable explanation is that the star grazed the limb and went through a depression. So disappeared, reappeared, disappeared. So just to illustrate that not only we can detect and measure size and shapes, But we can now do with Gaia, we can do geology. So this is Iapetus here. Iapetus is a body similar to Chyclo, and Iapetus has a ridge, an equatorial ridge, which is possibly a previous disk, a ring, which collapsed onto Iapetus and formed this ridge, which is about 50 kilometers across and 20 kilometers high, all around the equator. So if you project that at Chariklo, it's about 2 mass. So now Gaia has an accuracy of a fraction of a mass with a DR2 catalog, and using this updates of ephemeris using previous occultation, now you can go down to the Gaia accuracy. So you have an accuracy of a few kilometers from the shadow. So now we can start imagining putting small telescopes and say, okay, go there, and then the other person will go 5 kilometers or 4 kilometers away. So a picket fence approach. And then if, for instance, Chariklo has a ridge created by part of the ring which fell down onto the surface, we could detect that. It would be a test to see if Chariklo, like Iapetus, has a ridge. So you see that now we can send people, and we know that the occultation will take place there. And before we couldn't do that because we are not going to put in Chile 200 people from northern Chile to southern Chile, with most of them observing nothing. Another recent result, it was in August of this year. It was observed by an amateur astronomer, German amateur astronomer in Poshinger in Namibia. So we told him to observe Kawa occultation. So he let the instrument run for half an hour, and we could see here 10 minutes before the star disappeared behind something. And actually, when we looked at the motion of Quaoar satellite, which was discovered on different images before this occultation, WAIWAT, we saw that actually down to the accuracy of the orbit, this is consistent with the position of WAIWAT with respect to Quaoar. And an interesting issue is that the previous diameter of WAIWAT was about 80 kilometers, assuming it's the same albedo as Quaoar and just taking the ratio on the fluxes. So Quaoar is already quite dark. It's an albedo reflecting coefficient of about 11%. But because WAIWAT, because it lasted for 4 data points, it's at least 150 kilometers across. So it's about twice bigger as previously expected. So it's much darker actually than previously expected, assuming same albedo. So much darker means an albedo of 4%. So this would be one of the darkest objects in the solar system, which again, it's just impossible to do using images, because on Hubble imaging or sphere imaging or Keck imaging, you just see 2 points. You detect the Quaoar and the satellites, but you don't have any resolution on each of them. This was done in June of this year from the 10-meter telescope. So you see we are using 50 centimeter. I think the small of all was 10 centimeter telescope, and the biggest is up to now is 10 meters. So in Canarias, so we observed an occultation by Quaoar again, and we see a very sharp occultation, meaning that there is no atmosphere. I will show you the effect of the atmosphere right now. And Quaoar was the best candidate for having atmospheres besides Pluto or Triton, because it's big, it has some volatile elements on its surface, so it was a good candidate. But using this kind of observation, we can pin down the upper limit of any atmosphere less than 5 nanobars, which is 1,000 times smaller, less dense than Pluto atmosphere. So we can go very deep in the upper limit of such atmospheres. So talking about atmospheres of Pluto, there was a paper published this year on a survey of Pluto's occultation observed in the last 3 decades by many people, most of them amateurs actually in this list. So this is an example observed from ESO at their very large telescopes and with the NACO camera. So this is time here, is about 3 minutes. And here you see the star disappearance and reappearance, which is not sharp because the rays are bent, and then this creates a defocusing of the light and then a drop of signal which is not abrupt. You see some features here, gravity waves in the atmosphere of Pluto, and this is here the fluctuation in the Earth atmosphere. So here you see the Earth atmosphere fluctuations, and here you see Pluto's atmosphere fluctuations. So basically what's going on is that we observe from the ground, from Earth here, the stellar rays, and because they're deviated by the atmosphere of Pluto here, and because the atmosphere has a gradient of density, the rays are more and more bent, so all the energy going through this beam here is defocused in that wider beam, so this creates a drop of signal, which was used, for instance, so from some inversion techniques called Abel integrals, we can, from that drop of signal, have the density profile of the atmosphere, the pressure profile of the atmosphere, and from ideal gas equation we get the temperature profile. So we access at something which is just impossible to get without a method, because an image of Pluto from HST or any other instrument is just Pluto. You don't see the atmosphere. It's much too tenuous to see anything around Pluto on classical imaging. This is a profile of temperature versus distance to Pluto's center, observed by stellar occultation in black here. And this is a result from the radio science experiment on board of New Horizon during the flyby of 2015. So you see a very good agreement and some differences there, but that's now discussed. And here, the REX experiment is not sensitive enough to detect the atmosphere above that result. So not only we detect the atmosphere from Earth, but on a much wider span from very nearby the surface, not quite the surface, but up to 200 or 300 kilometers above the surface, while REX, here is not so complete. This is here the pressure with the surface here. So this is our best pressure profile we got for 2015. And these are the measurements by the REX experiment, the radio occultation experiment by New Horizon, near the surface and on the other side of the planet. So you see the good agreement between the occultation measurements and the New Horizon measurement. So this is gravity waves observed from New Horizon. So when you look at the sun from New Horizon back to the sun, you see these layers, and those layers are region with hazes, and the waves, gravity waves propagating the atmosphere will compress or dilute a bit these hazes. So the hazes are traces of gravity waves. So now we are starting to compare what we got from the ground with these features here and what's observed from New Horizon to model these gravity waves. Okay, so this is the evolution of Pluto's atmosphere with time, with different models, but just I'll be very fast. It's the years here. So in the last 30 years, you can see a very big increase of pressure on the surface of Pluto. And all the black dots are here occultation measurements, and those lines are models. So we are making constraining modeling. So it's kind of complex, but it just shows that very complex seasonal effect can be monitored by occultation over years and years, which cannot be done with a spacecraft, which go there for only once and cannot follow for years the evolution. So let me show you a central flash observed not by Pluto but using Triton. So this was the same kind of atmosphere as Pluto, and this was observed by an amateur in Portugal 2 years ago. So here you see Neptune, and here you see the star and Pluto, so you cannot distinguish them that too close together. And down here you have the light curve, the occultation light curve with time, which about 3 minutes. So you see the occultation by the atmosphere. Here you see only now at Triton, so the star is behind, but as you get close to the center of the shadow, you see this, which is a focusing of light by the atmosphere of Triton. So it likes a micro lensing, so the atmosphere is acting as a big lens. So not gravity lensing, but refractivity lensing, which is illustrated here. So this is a star, the image of the star, which is exaggerated here. So at some point you get a luminous ring around Pluto or Triton, and then the stellar image will flatten and then will assume its shape again. So it's very similar to what's called microlensing. And I will just finish in a few minutes a few comments on the rings discovered around small bodies. First ring discovered ever besides the giant planet was around Chariklo. It's a Centaur object coming from far away and now being moving between Saturn and Uranus. So it's called a Centaur object because it's all bunch of those bodies in that region. And then we discovered rings around another body which is much farther away, which is beyond Pluto, and then some dynamical works. So this is the discovery of Chariklo rings seen from La Silla in 2013. So this spans about 20 seconds here, and you have 10 points per second. So the Danish telescope was taking 10 images per second. And here you see the stellar flux, and we could see the star disappear for about 5 seconds behind Chariklo. And before and after that, we saw the star disappear, not completely behind something, and then behind something again, and you can see a secondary drop here. So we thought first it was cometary activity because Chariklo is an icy body, and some other bodies like Chiron are active bodies, they are creating jets and coma. So we first thought there were 2 jets, but after a while, because this was observed from Argentina, from Chile, and from Brazil, and all these people observed something, the star disappearing behind something, there. So after some days, we were forced to conclude that it was a very specific material surrounding the planet. And usually when you have material surrounding a body, you call it a ring. So we were forced to say, oh, it's a ring, even though we couldn't believe that because it's so small. It's so small, actually, that it's very, compare, for instance, to Saturn's ring. So you have a view in a smallish telescope from your balcony in Paris, for instance. This is a Hubble Space Telescope image of Saturn. This is a Cassini image, and here you can see the whole Chariklo system with its rings. There. Okay. So be careful, because one of my colleagues some years ago told me, oh, I didn't know Chariklo was orbiting Cassini division. And I didn't know there were rings around that satellite, so congratulations, Bruno, you are very smart. Say, no, it's a montage. So just to show you the scale, so it's really, really small rings. So it's a scaled version of Uranus or Saturn's rings, but with 2 orders of magnitude difference, okay? But even though it was the same for Haumea, so this is a real size, not angular now, it's real linear size of Haumea, which is a bit bigger than Pluto along its longest axis. And this is Chariklo at the same size. And this is a ring here, and the ring there, and Pluto, which has no rings. So it's pretty different from Saturn, because Saturn has a ring from very nearby to far away. And those rings are very narrow and kind of outside. So I started working on the dynamics of such body. If Haumea, for instance, is rotating very rapidly in 4 hours, so I started working on the dynamics of resonance between a rotating body with non-axis symmetric terms, like a galactic bar, moving in the center of the galaxy and creating resonances, Lindblad resonances in the disk of the galaxy and spiral waves. And these waves will create a torque between the bar and the disk, and this torque will create migration. And the question was, what is the effect on Chariklo rings? So this is a very simple model with Chariklo in the center, which is elongated, and this will create through some very simple friction law. It's a radial Stokes-like friction. So it's not really a collision, it's collision of the poor, because it dissipates energy, it conserves because it's radial angular momentum. So it's a good proxy for collisions, but it's not real simulation. But still, it shows, you cannot see it quite well here, but many of the particles inside the co-rotation radius, where the particles are moving at the same rate as Chariklo is rotating, moving down to the surface of Chariklo, and all the particles outside this co-rotation region is pushed away. And the main result of this is that they are pushed away beyond the outermost resonance, which is the 1 to 2, where the particle will make one revolution around Chariklo when Chariklo is making two rotations. So because of these strong torques associated with Lindblad resonances, the disk is forced to go either outside or onto the body. So the prediction of this model that the rings should exist pretty far away. So at some point we have a difficulty, because if you push a disk too far away, then it goes into the Roche limit, and then it accretes into satellites. So the ring will disappear not because the material disappears, but because it accretes into a satellite. So one criterion to have rings around a body, a non-axis symmetric body, is that the outermost resonance, which is 1 to 2 here, is inside the Roche limit. And to have this, the body must rotate fast enough, because if it's too slow, the 1 to 2 resonance will be far away and it will be outside the Roche limit, and then the disk will migrate, but then accretes into satellites and disappears as ring. And to make a long story short, actually, the criterion for the outermost resonance to be inside the Roche limit is related to the density of the particles in the ring particles, and the spin rate of the body. And if omega, the spin rate, is too slow, then you'll get unrealistic low densities from the ring particles. So this favors fast spinning bodies, so very high omega, so that to get some reasonable value for the density of the particles. So the prediction, another prediction of this result is that fast rotators should be favored to have rings, so maybe we should focus on those fast rotators first to detect rings. And this is now a simulation with real collisions that I started with a colleague of mine in Oulu University in Finland, Eiki Salo and his student. And they started a collisional narrow ring just inside the 2 to 3 outer Lindblad resonance. And after only 12 years, the ring has been pushed by the resonance just outside. And if you follow the time evolution, this is time here, and here's this 2 months, and you see the motion of the particle crossing the resonance and being pushed outside. So now we are trying to generalize this to other resonances, but the important thing is that this torque and this migration mechanism is working also with real collisions. not just a simple proxy of a radial Stokes force as was used before. So it's encouraging result because it shows that the mechanism is actually working for real collision between hard particles. Well, and I will finish get here. An interesting issue is that this is a sketch of Haumea shape and rings as discovered in 2017, 2 years ago. An interesting issue is that the radius of the ring is very close to the 1 to 3 or 2 to 6 resonance. So it looks like the ring particle are close to the resonance where they make one revolution around Haumea when Haumea is making 3 rotations. And when we look at Chariclo ring, it's also close to the 1 to 3 resonance. So it could be just coincidence because you see the error bars here. And so we don't really know because error bars are bigger than the location of the resonance, so it could be just coincidence. But still, we are now starting to see what is the effect of this 1 to 3 resonance on Chariclo rings on Haumea ring. Okay, so if you are interested in observing, go to the Lucky Star page, then choose your best object, your preferred object. You can put your limiting magnitude, and you can put also your position if you want. And so you have filters by dates. So if you are on vacations or free of some period, you can go there and put your interval of availability, your limiting magnitude, your object, and your place, and then you get maps. And because of Gaia accuracy, there are several occultations per day now all over the globe. So don't hesitate to go there, and some of them are interested in participating, just let us know. And go there, and if you want to see some of those objects, just go there and look at them. Also, if some of them know people, if you are from abroad, you can contact, so someone coming from Japan or well, any country in the world, can say, okay, in my lab or my institution, there are many observers, and we discovered that there are many observers actually. We're surprised the number, especially amateurs. So recently we realized that Romania has many observers. And we're surprised, and amateurs, and they're very serious and very dedicated. So don't hesitate to talk to us, talk to me, if your home country is hosting amateurs or professional people. Okay, thank you.
Okay, so thank you, Bruno. I just realized I forget to say that you just obtained an award for a prize, the Duato-Butté Prize at the Académie des Sciences from all this work. So congratulations, and we're happy to have you a few days after that. And now, are there any questions, any comments for Bruno? Yeah.
Non, peut-être, parce que les piles doivent être à plat. Non, les piles sont à plat pour le moment. Bruno, can you elaborate a little bit on your statement made at the start of your talk, namely that you were not concerned by seeing, for you the star is a point source. It's not real. I mean, the star has a shape, has a diffraction shape, and it's affected more or less by the atmosphere. So how are you removing these effects? Are you modeling them? What happened? There's something I missed there.
So first, concerning the size of the star projected to the body, it's usually a fraction of a kilometer. So it's if you have a very, very big telescope, you see the body, and then the stellar disk, which amounts to 1 kilometer less. So this is the ultimate
resolution is fixed by the star. And also, usually it's not actually the stellar diameter, but the Fresnel diffraction, which is also a fraction of a kilometer. Okay? Now, concerning, forgetting about this issue, which is the ultimate resolution, a fraction of a kilometer is stellar diameter or diffraction. Now, if the star is disappearing, you can fit the disappearance better than this effect. So you can go for the ingress and egress times something better than the size of the star. Now, concerning the seeing is just, a multitude of speckles. So when the star disappears, even the seeing is bad, everything disappears, okay? So if the seeing is very poor, but if the photometry is good, you are independent on seeing. Now, usually when the seeing is poor, the photometry also may be poor. But that different things, okay? Yeah. 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 Yes, but remember it's an on-off phenomenon. So as the star disappears, everything disappears, if the seeing is good or bad. Okay? So before the occultation, yeah, so when you have atmosphere, it's another issue because you really need quality. That's true. But if you have here 0, and then 0 here, okay? And when you fit with a sharp edge here, the accuracy of the timing will be set by the noise here. So if you see a point here, it could be just noise. But if you see a point here, you know that the star was half occulted here. And it's well above the noise here. Okay? So the timing accuracy you get eventually for the occultation is basically the signal to noise you have here times the integration time. So if you have 1 second integration time, and if we have 50% of the flux here, that you know that the star was half of the time in that bin, 2 within the noise here. Okay? Now, if you have an occultation by Pluto, and if the star is doing this, just from photometric fluctuation, that we don't know if you're looking at Earth atmosphere and Pluto's atmosphere. So when I showed you these spikes, it was on an 8-meter telescope in infrared, so seeing was very good. And you could see that the fluctuation in Earth atmosphere was much less than the fluctuations in Pluto's atmosphere. But on the smaller telescopes during that same night, we see big fluctuations, and then they are kind of not useless, but they cannot really probe the fine structure. So I agree that then the photometric is important, but not the size, of the star, okay? So if you have a very good seeing, then the ultimate resolution is linked to the acquisition time and the diffraction effect, and for some bright star, the stellar diameter.
I was wondering, so first of all, thank you very much for the talk, it was super interesting. I was wondering how you manage observations from, different amateurs. Like you showed the case of an observation from Namibia where from the observations you guessed that the rings had structure. So that's one observation. So something like that before having like a scientific conclusion, do you reobserve that? Like, do you want to confirm that hypothesis with other instruments or professional observations? And also, when you put everything together, I wonder how you treat, I guess each of these observations from amateurs have, how do you estimate the statistics, like the statistical error on the observation, the systematic error, yeah.
So for Chiclo and the structure inside Chiclo rings, we have been observing several of them. So the W feature, you can say once, okay, it's just noise, okay? But then this W feature has been repeatedly observed on bigger telescope, better signal to noise, and then the width of the ring has been shown to be variable on different places. So if you have only 2 measurements, you cannot tell, but if you have many measurements, you really see that it's out of the noise. So statistically, after a while, if you see repeatedly this W feature, if you see repeatedly that the width is not always the same, then you can conclude something. And that's why, depending on the size of the telescope, we can have higher acquisition rate. And on the biggest telescope, we ask for very high frequency, like 10, 20, or 30 images per second, and then we can see the features. Now, if an amateur tells us, oh, I have a 25 centimeter telescope, so we tell you, oh, you go there, you observe, blah, blah, blah. But at least you will get 1 point in the ring, and this will define precisely with the other points the orbit. So we don't really care in that case about the substructure of the rings, but about the general structure. So is the ring circular? Is it always the same radius? So we can do different things depending on the size of the telescope. It's like for the Pluto occultation I showed you before. If we had only one occultation from VLT, which is very high quality, but if you don't know where the center of Pluto is, then you can get very different numbers on the atmosphere, because it depends where the center of Pluto is. So it will move up and down the whole solution by many kilometers. Now, if an amateur observes from Colombia or from Venezuela or from Bolivia, blah, blah, you have not so good light curves, but they pin down where the body is. So having smaller telescope will help reconstructing the general shape, even though it doesn't give so many details, okay? So sometimes it's very good to have it's very important to have a good light curve, but per se, it's not the end of the story. So if you have one good light curve and then 5 amateurs elsewhere, then this will pin down the position, and the same for Chiclo rings. One will get the structure because it has bigger telescope and higher acquisition rate, and all the other amateurs will get the general shape, which is important too.
Any last questions? Yes.
So we see the improvement brought by Gaia, of course, and you said how much you've been helped by amateurs at different locations. Have you considered using fleets of small satellites that are observing Earth that can be potentially turned the other way to have more information and speedier ones? There's like 20 to 50 centimeters in a telescope, if I understand well.
Yeah, we did for Cheops, for instance. I've been talking with Cheops people, but the conclusion generally, and other projects, smallish telescopes around Earth, yeah. The problem is usually that small telescope and the orbit is not well known weeks in advance. So first, there are not so many events. So for Cheops, maybe we have 1 event per year, plus the fact that the orbit is updated every few weeks. So we cannot plan that. So the conclusion of all this that it could be interesting maybe once or twice, but it has nothing compared to 500 people observing from the ground, okay? Even with big telescopes. So it can add something, but it's not a big jump. So we have been even considering a dedicated satellite, but then you have to change all the time the orbit. So it implies a lot of, delta V, engineers, navigation issues. So then after a while, we'll spend just the time to redefine the orbit over and over. Excuse me? Yeah, you can have a fleet. But I don't want to spend my time just talking with engineers and updating the orbit every 2 weeks and observing, and then I prefer to secure, and have, I guess at some point it'll be done, but it's a lot of engineering time. So now with Gaia, there are several occultations per day over France. So tell people, just observe from your hometown, from Paris. While with a fleet of telescope, someone must be dedicated to this. It's a big job and a lot of money. You have to pay salaries for engineers. You have to launch the satellites. So it's the ratio now. It's not so favorable. Maybe it will sometime, but right now it's not really a big jump. But I mean, if you want to do this, you're welcome.